Yeah, good evening. Please, can you hear me? Hello, good evening. Can you hear me?
Can hear you, sir.
Yes, sir.
You guys should learn to speak louder. You just want me to be teaching the class as if I'm recording video for nobody. When question is being asked, you guys should respond. Let it be interactive. That's the essence of making it online. So if it is not live, there's no difference from when you are online and when you are not online. Why will be asking questions when you just keep quiet? You're not making difference from recording the video and just drop it then you watch. What's not the essence? So please God will assist us. Okay, so welcome to physics class. Let me share my screen now, and once you can see my screen, let me know. Okay, so can you see the screen now? Okay, now we are on question number 14, and the question was: a copper wire was subjected to a tensile stress of 7.7 times 10 to the power 7 Newton per meter square. Calculate the tensile strain of the wire if the Young's modulus equal 1.1 times 10 to the power 11 Newton per meter square. Alright, so if you look at this particular question here, you get to see that it's strictly under the topic called elasticity of material. Elasticity. So we are going to be looking at elasticity as a topic now. So we are going to consider elasticity as a topic. Elasticity. Okay, I think I should reduce the thickness of this pen. Now, when you talk about elasticity, what exactly do the examiner want to know as far as this topic is concerned? That is what they intend to test. Number one is that they want to test you if you understand the nature of materials. If you understand the nature of material. So when I say nature of material, we are talking about classification of material according to their elasticity. Are you getting it now? So that's the first thing that examiner want to test you on under this topic. And number two is that examiner wants to know if you understand the concept of Hooke's law. That is the law that binds the elastic nature of a material. Hooke's law. So, and then the third one is the characteristics of every elastic material. So, let's see how we can go on that and see the definition for each of the following. Now, when you say elasticity, what is elasticity? Elasticity is the ability of a material to elast. That is, when you apply force to a material, the ability of that material to extend or to compress is what we refer to as elasticity. So we define it as the nature of a material such that one application of force causes the material to deform. By removing the force, the material will return back to its original shape or size. That's what we refer to as elasticity. So I'll take it again. Elasticity is the ability of a material to regain its original shape or size after the removal of force. So when you apply force to a material and the material deforms, when you remove the force and the material returns back to its original shape or size, then you say the material is an elastic material. Do you understand that now? Now, when you now talk about classification of materials according to this elasticity nature, that is the classification of material according to their elastic nature, we have the following. We have brittle material. We have brittle material. We have ductile material. ductile material. And we have what we call brittle, what we call ductile, we have malleable materials. We have malleable material. Malleable material. Now, the question now is, what's the difference between all these materials? Brittle material, ductile material, malleable material. Remember we said it earlier that when we say elasticity, please guys, can you hear me?
Yes, sir.
Okay. So when we said it earlier that when we say elasticity, we are talking about the ability of a material to regain its original shape or size after the removal of force. Now with this property, we can categorize material into three: brittle material, ductile material, and malleable material. So when we say a material is brittle, we are talking about materials that break easily. Brittle materials, they are materials that break easily. They break easily. That is, before getting to their elastic limits, they already break. For example, glass, cast iron, ceramic, rocks, marbles, and high carbon steel. All these are material that we call brittle material. They break before they get to their elastic limits. Then when we say ductile material, ductile materials, they are materials that can be extended beyond their elastic limits before breaking. They are materials that can be extended beyond their elastic limits before breaking. They can be drawn into thin wires before breaking. Everything is now. So in most cases, if they want to ask you question using this ductile material, instead of them to say materials that can be extended beyond their elastic limits, they will say material that can be drawn into wire. So ductile materials, they are materials that can be drawn into wire. For example, we have mild steel, we have gold, we have copper, we have silver, we have lead, we have platinum. All these are examples of ductile material. Then the third one, what we call malleable material. Malleable materials, they are materials that can be built to shape. Materials that can be built to shape. That is what we call malleable materials. So any material that can build to shape is called malleable. For example, aluminium. So though to some extent we can say paper is also malleable, because you can bend paper to whatever shape you want. Such it is like aluminium. But why are we not giving paper as an example of material with malleability? It's because of the engineering characteristics of paper. So for the engineering students, they believe that any material that is said to be a malleable material, it has to be a metal that you can build to shape, not that you can fold to shape. Am I making sense now? Fine. So when you have a material always has the following. That is, for example, let's say I plot the graph of a material. So when you want to plot the graph of a material, you want to test the strength of a material or the nature of a material. For you to be able to test the nature of a material, you must plot the graph of stress against strain. So when you plot the graph of stress against strain, what happens? You are going to have a graph like this. Are you seeing it now? At this point, we have what we call E. At this point, we have what we call Y. At this point, we have what we call C. And at this point, we have what we call B. Now, all these points that are labeled E, Y, C, D, they can be labeled with any letter. they can be labeled with any letter, and that's the reason why I need to explain this for you. You see these 4 points that we have on this graph, they are what describe the nature of material that you are handling. Okay, so the first one is called elastic limit. That is the E. We call it elastic limit. And the second one, which is Y, we call it yield point. And the third one, which is C, we call it maximum load. The fourth one, which is B, we call it breaking point. Now, what's the meaning of all this? When you say elastic limit is the point beyond which an elastic material would not return back to its original shape or size. Are we together now? Elastic limit is the point beyond which an elastic material would not return to its original shape or size. That is what we call elastic limit. So what are they saying? What are they saying regarding this? When they say it is the point beyond which an elastic material would not return to its original shape or size. What it simply means is that once a material gets to this point, the material can still regain its original shape or size. But if a material should go beyond that point, that material will not regain its original shape or size. In that case, the material has become plastic. Then we have yield point. Yield point is the immediate point after the elastic limit, in which when the material gets to that point, the material has become a plastic permanently. Then we have maximum load. Maximum load is the point whereby further application of force on an elastic material would not result to further extension. Maximum load is the point whereby further application of force will not result to further extension. Then we have the breaking point. The breaking point is the point whereby an elastic material becomes permanently deformed. The material will what? Permanently deformed. That is what we call breaking point. I believe you understand this now, right? So, if that should be the case, we now want to compare how force, that is, when you apply force on elastic material, how does the force affect the extension? How does the force affect the extension? But before I go into that, there is this question that examiner usually asks on this particular graph. Examiner can tell you or ask you that when a graph of stress is plotted against strain, the slope under the linear portion of the graph is what? The slope under the linear portion of the graph is what? So when you plot the graph of stress against strain, you have that the slope is going to be given as stress divided by what? Strain. So stress divided by strain is given as Young modulus. So that is, when you plot the graph of stress against strain, the slope of the graph will result to Young modulus. Having said that, when you apply force to a material, the force applied to the material is going to what? Is proportional to its extension. And that is what Hooke's law states. So when you talk about Hooke's law states that the force applied to an elastic material is directly proportional to its extension, provided that the elastic limit is not exceeded. Provided that the elastic limit is not exceeded, when you keep applying force to a material, the extension will keep increasing. For example, if I have what? Let's take for instance that I applied a force of 5 Newton to a material, and that force causes extension of 2, let's say 2 centimeter. When I now apply a force of 10 Newton, it increased to 4 centimeter. If I apply a force of 15 Newton, it increased what? To 6 centimeter. What does this mean? You see that as I'm increasing the force applied, the extension is what? Is increasing. That means Hooke's law is being obeyed. So let's look at this. If I have that force is proportional to extension from Hooke's law, then I can say force is equal to Ke, where K is force constant, where K is force constant. And when you talk about force constant, what does force constant simply mean? Force constant means a unit force that will cause a unit extension. A unit force that will cause a unit extension. That is, force constant K is measured in Newton per meter. That's the unit, Newton per meter. You can write it as N over M, or you write it as Nm raised to power minus 1. So what does this mean? If I give you that the force constant of a string is equal to 20 Newton per meter, what this simply means, 20 Newton per meter, it means that for you to cause the material to extend by 1 meter, if I want the material to extend by 1 meter, then I need a force of 20 Newton. That is what force constant simply means. So force constant means what? The force that will cause a unit extension. So 20 Newton per meter means you need a 20 Newton force to cause what? 1 meter extension. So let's now take for instance that we are given that force constant of a material is 100 Newton per meter. If I want to extend the material to 10 meter, what amount of force will I need? I'm asking.
1,000.
I will need a force of 1,000 Newton. I believe you understand what they call force constant now, right?
Yes, sir.
Alright. So if that should be the case now, we can now what? Generate some equation for Hooke's law. So from Hooke's law, we have that F is equal to Ke, where F is what? Applied force. F is applied force in Newton. E is extension in meter, and K is the force constant. Now, this force can be anything. When I say anything, it can be anything. It can be a restoring force, it can be a gravitational force, it can be a centripetal force, it can be centripetal force, it can be energy. Are you getting it now? So the force can strictly be anything. So what you need to always watch out for is that in this question, what is this force pointing to? For example, if I give you that F is equal to negative Ke, given that F is equal to what? Negative Ke, what does this negative implies? Does that mean that the value has to be negative? No, that's not what it means. When you see this negative, it means that the force F is a restoring force. Force F is a restoring force. Now, what do you mean by restoring force? When you say F is a restoring force, what is it that will mean? Let's say I have what? I have a wire like this. This is the length of the wire. And then I apply the force to this wire, so the wire now extends to this point. Remember, this is the equilibrium position of the wire. The force that will take this body, it has extended beyond its normal position. The force that will take this body back to its original position is what we call a restoring force. And that's why we define a restoring force as a force that takes a body back to its what? Equilibrium position. Am I making sense now? So that's about what? About equation of Hooke's law. Still under Hooke's law, examiner can decide to ask you this question about Hooke's law. That is, if I plot a graph, let's say I plot a graph of F against extension. That is, when you plot the graph of F against extension, that is force against extension, you are supposed to have a straight line graph. So if you have a straight line graph, this symbolizes what? Hooke's law. And it's possible that you keep on applying the force until the material goes beyond its elastic limits. So if that should be the case, that means you are going to have some path to be curved. Now, question can come here. Let me label here A, and label here B, label here C, label here what? D. Examiner can ask you that at what point on the graph is Hooke's law obeyed? Are you getting that question now? At what point on the graph is Hooke's law obeyed? So you look at the graph, the point whereby there is a straight line. Are you getting it now? So the slope under the straight line obeys Hooke's law. That means Hooke's law is being obeyed between point A and then point B. That's one way of asking question under Hooke's law graph. Another way of asking you question under Hooke's law graph is that examiner can say, when the force is plotted against extension, when force is plotted against what? Extension, the slope of the linear portion of the graph is known as what? What is the slope of the linear portion of the graph? Can you guys hear me?
Yes, sir.
So when the person says that, what is the slope under the linear portion of the graph? The slope under the linear portion of the graph is going to be F all over E. So if the slope is F over E, remember, look at this equation. F equal KE. You see that K is equal to F all over E. Therefore, the slope under the linear portion of the graph is going to give us a force constant. These are tricky ways in which examiners do ask questions under Hooke's law. At times, they might make it kind of difficult for you. That they'll give you what? A graph, and the linear portion on the graph will be so small that it will be insignificant. Let's say you have something like this. I think I'm not really getting that. So let me try and sketch it. So at some point, if you look at this graph here, at some point you have a linear portion. So just look out and watch out for that place where you have a straight line. That is the point where Hooke's law is being obeyed. Is that taken now? Alright? So since we have understood Hooke's law, let us understand what we refer to as stress, strain, and Young modulus. Stress, strain, and Young modulus. Alright, so let's say, what is stress? When you say stress is given as the ratio of extension. The ratio of extension of an elastic material to its original length. The ratio of extension to original length is what we call stress. Then strain. Strain is the ratio of force applied on an elastic material divided by its area. The force applied on an elastic material divided by its area is called what? Strain. Then we have what we call Young modulus. Young modulus is the ratio of stress, the ratio of, there's a mix up here. When you say stress is the ratio of force applied on an elastic material to its original length. My bad, sorry. Stress is the ratio of force to original to its area. And strain is the ratio of extension to its original length. That's strain. So when you say Young modulus is stress divided by strain. Stress divided by strain is called Young modulus. The unit of Young modulus is Newton per meter square, and the unit of stress is also what? Newton per meter square, but strain has no unit. It has no unit because what? It is a ratio. Are we together now? Now, when you talk about Young modulus, when you say Young modulus, we can further break this down, since we know that, because in some cases, the person might not give you stress and strain. They might give you the force applied, they might give you the area, they might give you the extension, they might give you the original length, and then we ask you to look for what? Young modulus. Just understand that Young modulus in that case is going to become force divided by area, then divided by extension divided by original length. Far, near. You have that Young modulus is equal to FL all over what? AE. So whatever result you have here is going to be your result for the Young modulus. Force times original length divided by area all over divided by area times extension. So that's what we call what? Young modulus. Okay. So what other things? We also have some other modulus. Aside from Young modulus, we have some other modulus such as shear modulus, so we have other modulus such as shear modulus and bulk modulus. Alright, so that's fine. So Young modulus, we said it's given as what? Okay, now I want to quickly explain something before I move on. We have the word tensile stress. We have the word tensile strain. We have the word stress and we have the word strain. Now when you say stress, what does it mean? Tensile stress means a force that you use to compress something. When you compress something, we call it tensile. When you extend something, it is called stress. So tensile stress means compression, while stress means what? Extension. So just know the difference between the two. So in most cases, we always say Young modulus is equal to tensile stress divided by tensile strain. And we have what we call bulk modulus. Bulk modulus. So we have that bulk modulus is volume stress divided by volume strain. Are we done? Volume stress divided by volume strain. That is delta F over A divided by delta V over V. Or you say delta P, that is change in pressure, then delta V over V. So this is called what? This is called bulk modulus. So bulk modulus has value. Are you getting it now? And we majorly use it under when we are considering hydrostatic stress. So bulk modulus has to do with liquid. Young modulus has to do with solid. Bulk modulus has to do with liquid. And the third one, what we call shear modulus. That's another type of modulus. Shear modulus. So shear modulus is given as a shear stress divided by shear strain. So this one has to do with gas. Is that okay now? So that's that about what? The modulus of elasticity. So the last part of the notes is to talk about the energy stored in an elastic material. Please guys, do you understand everything I've said since morning? I'm asking a question now. Do you all understand?
Yes, sir.
Okay, so let's go to energy stored in an elastic material. So we have what? Energy stored in an elastic material. Energy stored in an elastic material. Alright, so when we talk about energy, we have that F times distance, that is force times distance, is going to give us work done. Abi? So this work done, because the definition of work done states that it is the work is the ability, that is energy is the ability to do work. That's the definition of energy. So that means that the amount of work you can do depends on the amount of energy you have. The amount of work that you can do, it depends on the amount of energy you have. So if you have least energy, it means you can do least work. So whatever work you've done is as a result of the energy that you have. If that should be the case, we can say work done is equal to what? Energy. And when we consider energy, we have what we call kinetic energy, which is 1 over 2 mv square, and we have what we call potential energy, which is mgh. mgh. So the energy stored in an elastic material, when you, for example, examiner always like asks us question about when we want to fire a catapult, what is the energy transition, that is transformation of energy in an elastic material. We have done that before when we are doing work energy and power. So how the energy converts. Are you getting it? So in most cases, examiner always asks us this question, whereby we want to compare potential energy with kinetic energy, or compare potential energy with the energy stored in an elastic material. So when we talk about the energy in an elastic material, we have that energy stored in an elastic material is 1 over 2 Fe, or you have it as 1 over 2 KE square, or you have it as 1 over 2 F square all over K. These are what we call what? Energy stored in an elastic material. So you have 1 over 2 Fe, 1 over 2 Ke square, 1 over 2 F square over K. So that is how we determine the energy stored in an elastic material. And you just need to memorize all of this so that when question is given, you are not just going to be familiar with just one formula, whereby if the question given to you is unable to help you, like the parameters in the question is unable to work with that formula that you are familiar. Let's say for instance that the formula you know is 1 over 2 Fe, and you are given a question that involves a force constant and extension. You don't know how to go about it. That's why we give you every other formula for what we call for energy stored in an elastic material. So this will be the last part of this particular topic, energy elasticity. So please, if you have a question, you can ask me now. You said what? I can't hear you clearly. I'm not hearing you clearly. The F stand for force, the K stand for force constant, the E stand for extension. Do you get that now? Any other question? I don't know if that is the question you asked because I couldn't hear you clearly. You said what?
Yes.
Okay. Alright, so let's go back to the main question that take us to this place before we start checking some other questions. Okay, or at first let's look at some other questions from Jamb and see how far we can go with it. Then we wrap it up by looking at the question that take us to this particular topic. Okay, so question number 1. The question is 1986 question number 2. 1986 question number 2. We have a graph like this, and the graph is a graph of force against extension. Then we have this. So that's how it looks. So the question says the figure shown is a graph of force against extension for a spiral spring. The force constant of the spring is given by the force constant of the spring is given by the A, slope of the linear portion, of the graph, B, length of the linear portion, of the graph, C, area under the linear portion, of the graph, and option D, area under the entire graph. So what will be the right answer? A, the slope of the linear portion of the graph. That's correct. Okay, so the next question here states that an additional load, this is 2008 question number 10. The question states that an additional load to an elastic material or elastic wire rather, to an elastic wire when the elastic limit is already reached when the elastic limit is already reached, will make the wire to A, break, B, be strained permanently, and C, recoil, and D, vibrate at high amplitude. So what will be the right answer to the question? What will be the right answer, guys? An additional load to an elastic wire when the elastic limit is already reached will make the wire to. So what will be the right answer?
B.
Be strained permanently. Be strained permanently.
B. Be strained permanently. So the material will strain permanently. That's correct. Okay, so the next question, 2012, number 15. 2012, number 15. The question states that if a load of 1 kilogram stretches a cord by 1.2 centimeter, what is the force constant of the cord? Take G equal 10 meter per second square. So option A, you have 866 Newton per meter. Option B, 833 Newton per meter. Option C, 769 Newton per meter. And option D, 667 Newton per meter. So what will be your answer? No. So what's the answer? If a load of 1 kilogram stretches a cord by 1.2 centimeter, what is the force constant of the cord?
B.
That is 833 Newton per meter. Is that what you have?
Yes, sir.
Okay, so that's correct. Do anybody understand how she got that, or we should solve it together?
So,
You said what?
solve it.
Okay. The question says that if a load of 1 kilogram, so the mass is 1 kilogram, stretches a cord by 1.2 centimeter, the extension is 1.2 centimeter. What is the force constant of the cord? We are looking for force constant K of the cord if G is 10 meter per second square. So for us to be able to answer this, we need to first of all convert the 1 kilogram force into Newton. Are we together now? So
Yes, sir.
to convert the mass to Newton, we multiply by gravity, abi? So mg is going to give us weight, which is in Newton. So that is 1 times 10, so that will be 10 Newton, right? And we convert the extension to meter, since we have the units to be in Newton per meter. So this one is going to be 1.2 divided by 100. So 1.2 divided by 100 will give us what? 1.2 times 10 raised to power minus 2 meter. So we can now say we have the relationship between force F and extension and the force constant. So we have that force constant is force all over what? Extension. So if that should be the case, we have what? 10 divided by 1.2 times 10 raised to power minus 2, which you can rewrite as 10 times 10 raised to power 2 divided by 1.2, and that will be 100 times 10, that's 1000, divided by 1.2, so you have 833.3 Newton per meter. So that will be the right answer to the question. I hope it's clear now.
Yeah.
Is it clear?
Yes, sir. It's clear.
Okay, so let's look at so let's look at another question, and this particular one is from 1982. Question 49. 1982, question 49. The question states that the point beyond which a stretched string does not return to its original shape or size, sorry, to its original length rather, is called the A, breaking point, B, elastic point, C, spring constant. D, elastic point. E, release point. So what will be the right answer?
Sir, A.
Elastic point.
A, breaking point.
Sir, A.
Is there nothing wrong with? Okay, sorry. Option B gives us elastic limit, not elastic point. Option B is elastic limit. So we are told that the point beyond which a stretched spring does not return to its original length is called the A breaking point, B elastic limit, C spring constant, D elastic point, E release point.
Elastic limit.
Elastic limit.
Limit.
So that's correct.
Limit.
Alright. So the next question states that 1987 question 14. The question is a load of 5 Newton. A load of 5 Newton gives an extension. A load of 5 Newton gives an extension of 0.56 centimeter in a wire which obeys Hooke's law. In a wire which obeys Hooke's law. Full stop. What is the extension? What is the extension caused by the load? What is the extension caused by a load? What is the extension caused by a load of 20 Newton? Option A, you have 1.12 centimeter. Option B, 2.14 centimeter. Option C, 2.24 centimeter. Option D, 2.62 centimeter. So what will be the right answer?
Start C. Yes.
C. That is 2.24 centimeter. You guys have the same result. Is there another person that, or is it the only one in class solving? We have more questions to look at. So 2.24 centimeter, that's correct. Does anybody want us to solve it?
Yes, sir.
Before we get to this point, I asked you if you understand. You said you understand. This question is so direct, and I see no reason why you should not be able to solve it. You are going for exam. If you fail to practice now, it's going to be a problem for you. It's not about me solving it for you, it's about you solving it yourself. Alright? So the question says that a load of 5 Newton, that is the force, is 5 Newton, F1, gives an extension of 0.56 centimeter. So it causes an extension of 0.56 centimeter in a wire which obeys Hooke's law. What is the extension caused by a load of 20 Newton? So we have another load of 20 Newton. and we don't know the extension caused by it. So if we want to obey Hooke's law, we therefore have that F equal KE, where K is the first constant. So we have that F over E is equal to K. So no matter what the force will be or the extension will be, the K will remain the same, since you are still dealing with the same wire. So if for F1 over E1 is equal to K, F2 over E2 is also equal to K, then we can conclude that what? F1 over E1 is equal to F2 over E2. So our F1 is 5 Newton divided by our what? E1, which is 0.56, equal to F2, which is 20 Newton divided by extension, which is E2, we don't know. So when you cross multiply, you have what? 5 Newton E2 equal to 20 times 0.56. What do you have? You have what? Or better still, don't worry. Let me just say 0.56 centimeter multiplied by 20 Newton. So divide those by 5. Sorry, divide those by 5 Newton. You have that E2 is equal to 0.56 centimeter multiplied by 4. Are you getting it now? So E2 is equal to 0.56 centimeter times 4. That will give us that is 2.24 centimeter. So that's how she got the answer. Is that okay now? Okay, so let's look at a question similar to that. Okay, so the question here is 1985 question 13. 1985 question 13. The question says that a force of 100 Newton stretches an elastic material, stretches an elastic string to a total length of 20 centimeter, if an additional force of 100 Newton stretches the string 5 centimeter further, find the natural length of the string. Option A, 15 centimeter. Option B, 12 centimeter. Option C, 10 centimeter. Option D, 8 centimeter. Option E, 5 centimeter. What will be your right answer? B.
15 centimeter.
Okay, that's option A, 15 centimeter. Who else again have 15 centimeter? So 15 centimeter is the right answer. Does anybody want us to solve it?
Yes, sir.
Alright. So we have that a force of 100 Newton stretches an elastic string to a total length of 20 centimeter. So let's say, because there might be need for us to use a diagram here. Let's say this is the string. This is the natural length of the string, L naught, while you have zero force applied on it. So when you now applied a force of 100 Newton, it causes this string to stretch by 20 centimeter. So this stretch by 20 centimeter. This is the equilibrium position. So from here to this place, it's now 20 centimeter. And when additional force is applied on it, that is another 100 Newton force, making it what? 200 Newton force on it. It extends it to, from here, it extends it by what? 5 centimeter further. So from here, it extends it to, this is 20 centimeter here. So from here to this place is what? 25. That is from here to this place is 25 centimeter. So we are asked to look for the what? This original length. So if I were you, I can do just a simple manipulation. If I remove this 100, this 5 will remove. Abi? It will remain what? 20. Isn't it? So if I remove this 100 again, when I remove 100 here, what will remove? 5 is what reduce. Abi? So that means if I remove 100 here, 5 will also reduce, making this one to become what? 15 centimeter. Do you understand that now? But if you don't understand that, is a thing you can do like this. The change in force 100 minus 0 divided by the change in the extension. That will be the change in the extension, that will be 20 minus L naught, that will give us the extension, equal to 200 minus 100 divided by 200 minus 100 divided by 25 minus 20. So this will become 100 all over 20 minus L naught equal what? 100 all over 5. So when you cross multiply, we have the 500 equal 100 into 20 minus L naught. So divide both sides by 100. This and this will cancel, and this will give us what? 5. So we have 5 equal 20 minus L naught. Collect the like terms. L naught is equal to 20 minus 5. So L naught equal what? 15 centimeter. Do you guys understand this now?
Yes, sir.
So that's how we get the 15. Okay, so let's move to questions under energy stored in a string. Energy stored in a string, or in a material rather. So questions under energy stored in a material is what we want to consider now. And the very first question that we have to consider here is 1994 question number 14. So the question says that a spring of length 25 centimeter is extended to 30 centimeter. Is extended to 30 centimeter by a load of 150 Newton attached to one of its ends. attached to one of its ends. What is the energy stored? What is the energy stored in the string? What is the energy stored in the string? Option A, 3,750 joules. Option B, 2,500 joules. Option C, 3.75 joules. Option D, 2.50 joules. So what will be the right answer to the question? C, 3.75 joules. Is that what everybody gets? So the correct answer is C. Alright, that's brilliant. So let's look at another question here. Another question is 1991, question number 7. The question states that a spring of force constant, 1,500 Newton per meter is acted upon by a constant force of 75 Newton. Calculate the potential energy. Calculate the potential energy stored in the spring. Option A, 1.9 joules. Option B, 3.2 joules. Option C, 3.8 joules. Option D, 5.0 joules. So what will be the right answer to the question?
C.
What is the answer?
C, 3.8.
3.8 joules. Okay, it's an answer. Do you have any other person? 1.9 joules. Any other person? Since we have two different answers now, that means there's need for us to look into it again. There's need for us to solve it together now. Okay, so the correct answer is 1.9. The correct answer is 1.9. So let's see. A spring of force constant 1,500 Newton per meter. So K is equal to 1,500 Newton per meter, and is added upon by a constant force of 75 Newton. So we have that F is 75 Newton. Calculate the potential energy stored in the spring. Remember, energy is what? Energy. So be it potential, be it kinetic. So they are always equal to each other. Am I making sense now? So since we are given K and we are given F, we have that the energy stored in the string is going to be 1/2 F square all over K. So that means 75 square divided by 2 times 1500. So 75 square will give us 5625 divided by 3000. So what will this give us? 1.875 joules, approximately 1.9 joules. So do you understand that now?
Yes, sir.
Okay. So let's look at questions under Young modulus and the cross-sectional area of a material. Alright. So this question is from 1992, question number 10. The question says that in an experiment to determine Young modulus, Young modulus, Young's modulus for a wire, several nodes are attached to the wire, and the corresponding extensions measured. The tensile stress in each case depends on a load and the extension. B, load and the radius of the wire. C, radius of the wire. And the extension. D, extension and the original length of the wire. So which will be the right answer there? B. That other person supports B. So that's absolutely correct. In an experiment to determine Young modulus for a wire, several nodes are attached to the wire and the corresponding extensions measured. The tensile stress in each case depends on, so it's going to depend on the radius, because tensile stress is going to be load all over area. So if you have load over area, for you to get area, you can say it is load over pi r square. So it's depending on the radius. I hope it's clear.
Yes, sir.
Okay. So the next question, 2011, question 14. 2011, question number 14. The question states that a copper wire was subjected to a tensile stress of 7.7 times 10 raised to power 7 Newton per meter square. Full stop. Calculate calculate the tensile strain. Calculate the tensile strain of the wire. Calculate the tensile strain of the wire. A, 7.0 times 10 to power minus 4. B, 2.2 times 10 raised to power minus 4. C, 2.0 times 10 raised to power minus 5. D, 7.0 times 10 raised to power minus 3. Take Young modulus. Take Young modulus as 1.1 times 10 raised to power 11 Newton per meter square. So what will be the right answer to that question? So what's the answer?
Sir A.
7 times 10 raised to power minus 4, Abi?
Yes, sir.
Okay, so that's correct. Is there any other person that does anyone go understand how we solve this? And I think that's the question that brought us to this topic, right? Yeah, I think so. Let me check. So that's the question. Question 14, a copper wire. So the correct answer is here is option D. Yeah, I think the paper type is different. So this 7.0 times 10 raised to power minus 4. Okay. Okay, so can you answer this question? We've done the topic, density and upthrust. We've done that. Question 15. Question 15. The question states that an object weighs 22 kilogram in water. An object weighs 22 kilogram in water and 30 kilogram in air. What is the upthrust exerted by the liquid on the object? So what will be the right answer to that question? So I'm asking before we move to the next topic. I can't hear you. B, that is 50 Newton. 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 50 New Okay, somebody said 50 Newton. Do you have another person?
Star 8.
I can't hear you guys clearly. It seems your network is somehow.
Star 8.
Hey, that is
8.
80 Newton. Okay, do you all agree with her? Do you all agree with her? 80 Newton. Okay, let's see. Now, when we want to look for the up thrust on an object, so the weight of the object in air so the question is that 22 kilogram. When you convert 22 kilogram to what, to Newton, that will be 220, right? So 220 minus what is it called? Minus 300. That's 300 minus 220. So the correct answer is what? 80 Newton. So that's correct. Absolutely. Well done. Okay. So our next question is question number 16. So the question states that a block of aluminium is heated electrically by a 30-watt heater. If the temperature rises by 100 degrees Celsius in 5 minutes, the heat capacity of the aluminium is. So this is going to be the topic that we are going to continue with in our next class. That is heat and its measurement, where we look at heat capacity and specific heat capacity. Okay, so till then, I believe we are moving. We are getting very close to the end of the all of the questions. So, and I think we have covered more topics now. Okay, guys. So, any questions so far on the topic that we are able to cover today? Do you have questions?
Sir, I have a question.
What was the
How do you
question?
calculate up thrust?
How do you calculate up thrust?
Yes.
So, up thrust is original what weight, that is the actual weight, minus the apparent weight. Apparent weight simply means the weight displaced by water. So actual weight is, if you look at the body now, the actual weight is the weight that you have in air. When you have 30 kilogram in air, this is the actual mass of the body. And when you have 22 kilogram in water, this is apparent weight. Are you getting it now? So it's because the object experience up thrust, that's why the mass reduced to this point. So for you to know the up thrust, that is the what? The lost in weight. So the lost in weight is what they call up thrust. And that will just be the weight in air minus what? The weight in water. So this will give us what? 8 kilograms. So if you convert 8 kilograms to Newton, you have what? 80 Newton. Do you understand that now?
Yes, sir.
Okay. So up thrust simply means lost in weight. Any other question? Okay, so in the absence of no question, thank you for making it to today's class. See you guys tomorrow. I think your next physics class is when? Maybe Friday, I don't know. Okay, so till then, read your book and